Okay, so now that we know how to take derivatives of exponential functions, we're going to use this to see where the derivative of logarithmic functions come from. So first I'm actually just going to give you the definition. So whenever we're deriving the natural log of x, we simply get 1 over x as its derivative. And of course, watch out for the chain rule. Same idea there. So if it's ln of u, where u is some function, then we get 1 over u times u prime. Okay? But where does this come from? So we're going to use implicit differentiation to prove that the derivative of natural log of x is in fact 1 over x. Okay, now you don't ever have to recreate this because this one's not too hard to remember, but I want you to understand where things come from in this class, so that's why I'm going to show you real quick. Okay, so let's say we have y equals natural log of x. And we're going to first rewrite this in exponential form, since that's what we do understand how to take the derivative of. So first let's change it to exponential form. So remember to do that, we're thinking e raised to some power y gives us x. Okay, again, logs are exponents. So whatever the log of x is the exponent. So that's why y ends up here. Now, let's derive implicitly. And don't forget your chain rule. All right, so the derivative of e to the y is itself, that y looks kind of weird, y, times the derivative of that inside function, which means we get a dy dx showing up. And then the derivative of x is simply 1. Thus, if we solve for dy dx, we get 1 over e to the y, and guess what? E to the y equals x. So this is how we end up with the derivative of natural log of x equaling 1 over x. Okay, so that's where it comes from. You don't necessarily need to be able to do that, but I just like having some sort of explanation behind it. So let's just do 2 quick examples. So example 1 is we're going to find y prime if y equals, this is not, you know what, we're going to be proper. Find y prime if y equals the natural log of 2x plus 2. Okay, so then if we derive this, we will simply get that dy dx equals derivative of the outside. The derivative of natural log is 1 over that thing, whatever we're taking the natural log of. And we do not change that thing when we plug it in, right? Then we derive by the derivative, then we multiply by the derivative of the inside with parentheses, since we have more than one term, so that's going to be times the derivative of 2x plus the derivative of 2. So I'm just getting a times 2 here. Not as exciting as I thought it might be. So I'm going to get 2 over 2x plus 2, which of course you can simplify if you like. So we'll get y prime is 1 over x plus 1. Beautiful. All right, example 2. Okay, so let f of x equal, you're going to like this one, natural log of tangent x. Find f prime of x. Okay. Let's think about this. This is, again, the chain rule. Just like with trig, natural logs almost always have a chain rule going on because it's rarely just an x in here. So the derivative of the outside is the 1 over whatever is the inside, unchanged, times the derivative of our inside, which is tangent x. And we definitely remember that that derivative is secant squared x. So we're going to get f prime of x equals secant squared x over tangent x. Now, just be careful. You may see this as an answer choice. Sometimes with these types of functions, people rewrite them. So in this case, you could rewrite secant squared x as 1 over cosine squared x. Rewrite tangent here. And you can see that we're going to be able to simplify in a way. So some people would consider it simplifying, some people wouldn't, because then that's just going to give us 1 over sine x cosine x, which is also the same as what? Cosecant x, secant x. So I'm just reminding you of how things can be a little tricky. I know, I hate myself. Sometimes when we're doing these problems with how they can be simplified. Okay, one last example. So we can sometimes have bases other than the natural log, although we do not use them that frequently in this class. But I am going to show you that I don't really want you to memorize a different rule. We're going to use the same properties, but also with a little bit of log properties. So if you remember, there was something called the change of base set up whenever you were in pre-calculus. And it allows us to rewrite this as some sort of fraction. And we can choose whatever base we want. So I'm going to change it back to natural log so that I don't have to deal with this random base of 5. So we get natural log of x squared over natural log of 5. And then we're going to derive this, because now I actually understand it. And this is just a constant, right? Natural log of 5 is just a number. So I'm actually going to bring that out front, like as a constant multiple. A really ugly constant multiple, but it is just a constant multiple. Okay. And then there's, again, more than one way you can approach this, right? You can leave it in this form and do the chain rule, which is what most of us would probably do. So let's just see what that would look like. So we would leave this guy out front times the derivative of natural log of x squared, that'd be 1 over x squared, times the derivative of x squared, which is 2x. And this we could simplify, right? So let's see, the x is going to cancel out one of the x's here. So we would be able to simplify this here. One of this x would cancel out one of the ones in the denominator, and we'd be left with a coefficient of 2 over ln 5 times 1 over x. And you could leave it that way, or you could just write it as one big, lovely expression. Okay? You also could have simplified, and a lot of times this is encouraged, simplify before you derive if you can. And here we could have used the power rule and brought the 2 down front as a multiple and gone ahead and made this really beautiful constant out front. And then that would have just left us with the natural log of x to derive, which is even easier. Because we know we'd have this constant unchanged, and then the derivative of ln x is simply 1 over x. So it kind of saves you from the chain rule, which we very often mess up, which is a reason you'll hear me ask you to try to simplify as much as we can before deriving. And that's it.